Hello there, and welcome to the Sleep Journal. Tonight, we are going to talk about something so small, it should not matter at all, and yet it is everywhere. Cosmic dust. Not the dust that gathers on a shelf. Not the dust a broom sweeps into a corner. This is dust on a completely different scale, tiny grains of rock, carbon and ice, some no wider than a strand of smoke, drifting through the space between the stars. It sounds like nothing. A speck. A fleck. Something too small to notice. But cosmic dust is not nothing. It is the raw material of everything. Every star you have ever looked up at once began its life as a cloud of this dust, slowly gathering itself together under gravity, over millions of years, until it became dense enough and hot enough to ignite. Every planet, including the one you are lying on right now, formed from a spinning disk of dust, left over after a star was born, grain sticking to grain, pebble sticking to pebble, until worlds took shape. And every atom in your own body, the carbon, the oxygen, the iron in your blood, was forged inside a star, and then scattered into space as dust, long before the sun, or the earth, or you, ever existed. Tonight, we are going to follow that dust. From the death of ancient stars, to the birth of new ones. From the thin haze that glows faintly above the horizon before sunrise, to grains older than the sun itself, locked inside meteorites that fell to Earth. Before we begin, if evenings like this help you drift off, feel free to like, subscribe, or leave a gentle comment below. It helps other tired minds find their way here. But for now, there is nothing you need to do. Let your jaw unclench. Let your shoulders drop. Let your breathing slow down into something easy and unhurried. And as your mind begins to soften, join me. Let us begin. Scientists estimate that our galaxy alone contains an amount of dust equal to tens of millions of times the mass of the sun, spread across a disk 100,000 light-years wide. Most of that dust is astonishingly thin. In many regions of interstellar space, there might be only a single dust grain within a volume the size of a small room. And yet, thin as it is, this dust is dense enough, patient enough, and old enough to have shaped nearly everything we can see in the night sky. It absorbs starlight. It reflects it. It blocks it, carving dark lanes across the bright arc of the Milky Way. And slowly, over unimaginable stretches of time, it collapses under its own gravity and becomes something new. A star, a planet, a quiet world, spinning gently, somewhere in the dark. It is worth sitting with how strange this really is before we go any further tonight. When most people picture the vastness of space, they picture emptiness. Black, silent, and essentially featureless, except for the occasional bright point of a star. And in many ways, that picture is correct. Space genuinely is close to empty, far emptier than the finest vacuum any laboratory on Earth could ever produce. But close to empty is not the same as completely empty. Scattered through that vastness, in concentrations so low they barely register, are these countless tiny grains, left behind by generation after generation of stars, drifting patiently, waiting their turn to become something else. Tonight, instead of thinking about the stars themselves, the bright, dramatic endpoints of stellar life, we are going to spend our time with something quieter, and in many ways more patient. The dust in between, the raw material. The part of the story that rarely gets told because it does not shine, and does not explode, and does not announce itself in any dramatic way at all. It simply drifts, slowly, for as long as it needs to, until its moment finally comes. To understand where cosmic dust comes from, we have to start with the death of a star. Most of the heavier elements in the universe, everything beyond hydrogen and helium, were not present at the very beginning of time. They were built later, inside the cores of stars, through nuclear fusion, as those stars burned through their fuel over millions or billions of years. Carbon, oxygen, silicon, iron, all of it was cooked slowly, in stellar furnaces, layer by layer, over the long life of a star. But those elements do not simply stay locked inside the star forever. When a star reaches the end of its life, it releases much of that material back into space. For a star like our sun, this happens gently. In its final years, as it swells into a red giant, and gradually sheds its outer layers into space, forming a glowing shell known as a planetary nebula. For much larger stars, the ending is far more violent. They explode as supernovae, blasting their contents outward at incredible speed, scattering newly forged elements across enormous distances in a matter of seconds. In both cases, gentle or violent, something remarkable happens in the expanding, cooling material. As the gas drifts outward and cools, atoms of carbon, silicon, oxygen, and other elements begin to find each other. They bond together, forming tiny solid particles, grain by grain, in much the same way that frost slowly forms on a cold window on a winter night. This is the birth of cosmic dust. It condenses directly out of the outflow of dying stars, the same way steam condenses into droplets of water as it cools in the air. Astronomers have actually watched this process happen, using infrared telescopes trained on stars nearing the end of their lives. They have seen the telltale signature of dust forming in real time, appearing gradually in the outer layers of aging stars and in the debris of recent supernovae. One particularly striking example came from the study of the supernova known as SN 1987A, observed in a nearby galaxy called the Large Magellanic Cloud. Years after the explosion itself, astronomers detected large quantities of newly formed dust within the expanding remnant, far more than expected, confirming that a single supernova can seed the surrounding space with an enormous amount of raw material. Multiply that by the billions of stars that have lived and died across the history of our galaxy, and you begin to understand where all this dust actually comes from. It is quite literally the ash of dead stars, drifting slowly through the dark, waiting for its next chapter to begin. The rate at which this happens varies enormously depending on the type of star involved. A star similar in mass to our own sun will spend roughly 10 billion years quietly fusing hydrogen into helium, before finally swelling into a red giant and shedding its outer layers relatively gently over a period of thousands of years. A much more massive star, 10 or 20 times the mass of the sun, burns through its fuel far more quickly, sometimes in only a few million years, before ending its life in a single, catastrophic supernova explosion. These massive, short-lived stars are disproportionately important dust producers because supernovae are capable of forging and scattering vastly larger quantities of heavy elements in a single event than a smaller, gentler star could ever produce across its entire lifetime. Astronomers studying supernova remnants have found dust particles ranging enormously in size, from grains far smaller than anything visible under an ordinary microscope, up to somewhat larger clumps, though nearly all of it remains, by everyday standards, extraordinarily fine. Once released, this dust does not remain near its parent star for very long, at least not on cosmic timescales. Stellar winds, radiation pressure, and the slow, steady rotation of the galaxy itself all work together to disperse this material outward, mixing it gradually with the broader interstellar medium, until, over the course of many millions of years, it becomes almost impossible to trace any single grain back to the exact star that once produced it. Once dust drifts out into interstellar space, it does not simply sit still forever. Over millions of years, gravity slowly pulls scattered gas and dust together into vast, cold clouds. Astronomers call these molecular clouds because within their cold, dense interiors, atoms can bond into molecules that would be quickly destroyed almost anywhere else in space. These clouds can stretch for hundreds of light years and contain enough material to form hundreds of thousands of stars like our sun. Within a molecular cloud, dust plays a role far more important than its tiny size would suggest. Dust grains act as a kind of meeting place, a surface where atoms and molecules can land, stick, and react with each other, forming more complex molecules than could ever form freely floating in open space. Some of these dust grains even become coated in thin layers of ice, frozen water, carbon monoxide, and other compounds, built up slowly over thousands of years in the extreme cold of the cloud's interior. Dust also plays a second, equally important role. It blocks light. A dense molecular cloud, thick with dust, can be almost completely opaque to visible light, appearing to us as a dark patch against the brighter background of the galaxy. This is why some of the most famous features of the night sky, dark, star-obscuring lanes running through the Milky Way, are not empty space at all. They are simply regions thick with cosmic dust, hiding whatever lies behind them from ordinary telescopes. Deep within one of these dark, dusty clouds, gravity slowly begins to win. A particularly dense clump of gas and dust starts to collapse in on itself, drawing in more material as it shrinks. As it collapses, it spins faster, flattening into a disk, and heats up at its center. Eventually, if enough material gathers, the center becomes hot and dense enough to ignite nuclear fusion. A new star is born. But the story does not end there. Around that newborn star, a thin disk of leftover gas and dust continues to swirl, a structure astronomers call a protoplanetary disk. Within that disk, the same dust that once floated freely through interstellar space now begins a very different journey, one that will eventually lead to the formation of planets, moons, asteroids, and comets, all built, quite literally, from the accumulated dust of long-dead stars. Molecular clouds themselves are surprisingly cold places, often only a few degrees above absolute zero, the coldest temperature theoretically possible. At those temperatures, chemistry behaves very differently than it does here on Earth. Reactions that would happen instantly at room temperature can take thousands of years to occur within a molecular cloud, simply because atoms and molecules are moving so slowly and colliding so rarely in such thin, cold surroundings. This is precisely why the surface of a dust grain becomes so important. It gives wandering atoms a place to land, and enough time sitting still, pressed gently against that surface, for a reaction to finally occur that might otherwise never happen at all in the open cold of space. Over the past several decades, radio telescopes tuned to detect the faint chemical signatures of molecules within these clouds have identified an astonishing range of compounds drifting through them. Simple molecules like water and carbon monoxide, but also far more complex organic compounds, some of them remarkably similar to molecules found in the chemistry of living things here on Earth. This has led some scientists to wonder whether the earliest chemical building blocks of life itself might have first assembled not on a young planet at all, but earlier still, quietly, patiently, on the cold surface of an ordinary grain of interstellar dust. The process by which dust becomes a planet is one of the most patient stories in all of astronomy. It begins with grains barely larger than particles of smoke, drifting within the protoplanetary disk surrounding a young star. Through gentle collisions, these grains begin to stick together, held by weak electrostatic forces, similar to the static electricity that makes dust cling to a balloon. Over time, these fragile clumps grow larger, from grains to pebbles to rocks the size of boulders. This early stage of growth remains one of the more mysterious steps in planet formation, because at a certain size, objects should, in theory, start bouncing off each other rather than sticking, or even shatter on collision rather than merge. Yet somehow, across countless young solar systems observed throughout the galaxy, this barrier is regularly overcome, and growth continues. Once objects reach roughly a kilometer across, gravity itself takes over as the dominant force. These larger bodies, called planetesimals, begin pulling each other together through their own gravitational attraction, growing steadily larger through repeated collisions and mergers. Over a period of millions of years, this process can build objects the size of small moons, and eventually, full-sized planets. Every rocky planet in our own solar system, including Earth, formed this way, built gradually from the same dust that once drifted freely through interstellar space, slowly gathering together around our infant sun, roughly 4.5 billion years ago. Even the planets that did not form primarily from rock, the gas giants like Jupiter and Saturn, owe their existence to dust. Their solid cores likely formed first, through the same dust accumulation process that built the rocky planets, growing large enough that their gravity could then pull in vast quantities of surrounding hydrogen and helium gas, forming the massive atmospheres we see today. Even comets and many asteroids preserve, in a sense, a more primitive stage of this process, remaining relatively unchanged since the earliest days of the solar system. Some comets are essentially loose collections of dust and ice, held together weakly enough that a close pass by the sun can cause them to shed material, forming the long, glowing tails that have fascinated observers throughout human history. In every one of these objects, planets, moons, asteroids, and comets, the same basic material persists: ancient dust, formed in the winds of dying stars, patiently reorganized over billions of years into the worlds we now call home. It is worth pausing on just how long this entire process takes, from beginning to end. From the moment a molecular cloud first begins to collapse, to the moment a fully formed planetary system settles into a stable configuration, several million years typically pass. An almost unimaginable stretch of time by human standards, and yet remarkably brief when measured against the roughly 10 billion year lifespan of a star like our Sun. Astronomers have been fortunate enough to observe many young solar systems at different stages of this process, scattered throughout nearby star-forming regions, giving them something like a series of snapshots, each one capturing a slightly later moment in what is essentially the same long, patient story. Some young systems still show enormous, thick disks of gas and dust, largely unchanged, surrounding stars only a few 100,000 years old. Others show disks with clear, empty gaps carved into them, likely marking the locations where planets have already begun to form, gravitationally sweeping their orbital paths clear of remaining debris. Still others, somewhat older, show disks that have thinned dramatically, most of their original material already gathered into planets, leaving behind only a faint, sparse remnant, similar to the thin disk of dust that still lingers, even today, within our own solar system. Cosmic dust is not one single, uniform substance. It comes in several distinct varieties, each with its own origin and its own chemistry. The most common type is known as silicate dust, made primarily of silicon and oxygen, bonded together in mineral structures, similar to the sand and rock found on Earth. Silicate dust tends to form around cooler, oxygen-rich stars, condensing out of their outer atmospheres as they age and shed material into space. A second major type is carbon dust, sometimes called soot in a very loose sense, formed around carbon-rich stars, where carbon atoms bond together into complex molecular structures rather than combining with oxygen. Some of these carbon-based grains contain structures remarkably similar to graphite, or even to complex ring-shaped molecules known as polycyclic aromatic hydrocarbons, compounds that are surprisingly common throughout the galaxy, and that some scientists believe may have played a role in the earliest chemistry that eventually led to life on Earth. A third important category is icy dust, grains that formed a solid silicate or carbon core early on, and later became coated with thin layers of frozen water, carbon dioxide, ammonia, and other simple compounds. In the extreme cold of dense molecular clouds, these icy grains are especially important in the outer regions of forming solar systems, far from the warmth of a young star, where they become the building blocks for icy moons, comets, and the frozen worlds found at the edges of many planetary systems, including our own. Interestingly, the type of dust found in a given region of space can tell astronomers a great deal about the history of that region. A dense concentration of silicate dust might indicate the remnants of an aging, oxygen-rich star nearby. A patch rich in complex carbon molecules might point toward the debris of a very different kind of stellar death. By carefully studying the infrared light absorbed and re-emitted by these different dust types, astronomers can effectively read the chemical fingerprints scattered throughout the galaxy, piecing together a kind of cosmic archaeology, tracing individual grains of dust back toward the specific type of star that likely produced them, sometimes billions of years in the past. It is a remarkable thought that a single grain of dust, drifting silently through the darkness between stars, might carry within it a tiny preserved record of a star that died long before our own sun ever began to shine. The physical size of these grains also varies considerably, though nearly all of them remain far smaller than anything visible to the naked eye. Many interstellar dust grains measure somewhere between a few hundredths and a few tenths of a micron across, smaller than the wavelength of visible light itself, which is part of why they interact with light in such particular, distinctive ways, scattering blue light more efficiently than red, and absorbing certain wavelengths almost completely, depending on their precise composition and shape. Some grains are roughly spherical, others, particularly certain carbon-based structures, form elaborate, layered shapes, sometimes compared to tiny, imperfect onions, with alternating layers built up slowly over long periods of exposure to different chemical environments as the grain drifted through varying regions of space. Scientists studying these structures under powerful electron microscopes, using tiny samples recovered from meteorites or captured directly from comets, have found grains with astonishingly intricate internal structures, layer upon layer, each one recording a different chapter of that particular grain's long, slow journey through the galaxy, sometimes stretching back well over 4.5 billion years. You are lying very still now. The day has grown distant. The thoughts that pressed close earlier have begun to soften at their edges. Your breathing has found its own pace. Slow, easy, unhurried. And as you rest here, I want you to imagine drifting, very gently, through a vast, quiet cloud of cosmic dust, somewhere between the stars. There is no sound here, because sound cannot travel through the emptiness of space. There is only a faint, soft glow, distant starlight scattered gently by countless tiny grains, filling the darkness around you with a dim, silvery haze, like moonlight filtered through a light morning fog. The dust here is impossibly thin, spread out across trillions of miles, and yet somehow it still catches the light just enough to soften the darkness, just enough to make the emptiness feel less empty. Imagine floating slowly through that hazy light, weightless, unhurried, with nowhere you need to be. Each tiny grain around you has traveled here across an unimaginable distance, carried by the wind of some ancient, long-vanished star, drifting patiently for millions of years, with no destination in mind, simply following the slow, quiet pull of gravity, wherever it happens to lead. There is something deeply calming in that patience. This dust is not in a hurry. It does not worry about where it is going or when it will get there. It simply exists, drifting, waiting, content to let time do its slow work. Let your body borrow a little of that patience now. Let your shoulders soften and sink deeper into the bed beneath you. Let your hands rest, heavy and still, exactly where they are. There is nothing you need to do right now, and nowhere you need to be. Just this soft, silvery haze, and your own slow breathing, blending together the way a single grain of dust blends quietly into the vast, gentle cloud that surrounds it. Somewhere far ahead of you, deep within this same drifting cloud, a small, dense knot of dust and gas is slowly beginning to collapse under its own gentle gravity. The first quiet stirrings of a star that will not be born for hundreds of thousands of years yet. There is no rush here, no deadline, only the slow, patient unfolding of something vast, taking exactly as long as it needs to take. And you, resting here tonight, are allowed exactly that same patience, exactly that same permission to simply drift, softly, towards sleep, taking exactly as long as you need to take. Notice, too, how little this quiet cloud around you seems to want. It is not reaching for anything. It is not striving towards some distant goal, or measuring its progress against any deadline. It simply continues existing, exactly as it is, at exactly the pace that feels natural to it. And that alone seems to be enough. There is no part of this vast, drifting cloud that is anxious about tomorrow, or replaying yesterday, or wondering whether it is doing things correctly. It simply is, patiently, quietly, without effort. Let that same quality settle into your own body now, layer by layer. Let your forehead soften. Let your jaw loosen just a little further. Let your chest rise and fall without you needing to guide it at all, the way this dust drifts without needing to guide itself either. Somewhere in this same vast cloud, other travelers exist too, closer together in places, forming faint, ghostly wisps and threads, then thinning out again into near total emptiness. And yet the entire cloud somehow holds together, loosely, gently, connected by nothing more than the soft pull of gravity working patiently across unimaginable distances and unimaginable time. Not all cosmic dust lies far away, among distant stars. Some of it is much closer than you might think, drifting quietly through our own solar system, scattered along the same orbital plane where Earth and the other planets travel around the Sun. This nearby dust comes from comets, which shed material every time they pass close to the Sun, and from collisions between asteroids in the belt between Mars and Jupiter. Over billions of years, this debris has spread into a broad, thin disk of dust, extending outward from near the Sun, all the way past the orbit of Mars. Under the right conditions, this dust becomes visible to the naked eye, in a phenomenon known as zodiacal light. On a clear, dark night, away from city lights, in the hour or two just after sunset, or just before sunrise, a faint, softly glowing cone of light can sometimes be seen rising from the horizon, along the same path the sun and planets travel across the sky. This glow is sunlight, scattered gently off countless tiny particles of interplanetary dust, each one no larger than a fine grain of sand. Ancient civilizations noticed this glow long before they understood what caused it. Some cultures described it as a false dawn, a soft light appearing before the true sunrise. Persian astronomers gave it a name that translates roughly to the light before the light. It was not until the 17th century that European astronomers began seriously studying the phenomenon, and not until much later that its true source, countless grains of ancient dust scattered throughout our solar system, was properly understood. This dust does not stay in place forever. It is constantly being replenished by comets and asteroid collisions, and constantly being lost, slowly spiraling inward toward the sun over thousands of years, pulled by a subtle effect of sunlight itself, known as the Poynting-Robertson effect, in which the gentle pressure of sunlight causes small particles to gradually lose orbital energy and drift inward. Eventually, much of this dust either falls into the sun or is swept away entirely by the solar wind. Yet somehow, this cosmic reservoir remains remarkably stable over long periods of time, because new debris is being generated constantly, ensuring that on quiet, clear evenings, that faint ancient glow continues appearing along the horizon, largely unchanged, just as it has for as long as human beings have been looking up at the sky. The zodiacal light is not the only visible trace of this nearby dust. Under exceptionally dark skies, far from any artificial light, careful observers have occasionally reported an even fainter glow, appearing directly opposite the sun's position in the sky, known as the Gegenschein, a subtle brightening caused by sunlight reflecting almost directly backward off dust particles positioned precisely behind Earth in its orbit. This effect is so faint that it remains genuinely difficult to observe, even under ideal conditions, and many experienced amateur astronomers report never having seen it clearly in an entire lifetime of observing. Together, the zodiacal light and the Gegenschein form a faint, complete ring of scattered sunlight, tracing the entire plane of our solar system's dust disk across the sky, largely invisible in ordinary conditions, but quietly present, night after night, a soft reminder that even the space immediately surrounding our own planet is not truly empty at all, but gently filled with the slow, ancient debris adding to this thin, glowing disk for billions of years. Studying dust that is scattered across such vast distances presents a real challenge for scientists, because in most cases, they cannot simply travel out and collect a physical sample. Instead, astronomers rely primarily on light, specifically infrared light, to study the properties of interstellar dust from a great distance. Dust grains absorb visible light from nearby stars, warm up slightly, and then re-emit that energy as infrared radiation, a wavelength invisible to the human eye, but easily detected by specialized telescopes. By carefully analyzing this infrared glow, scientists can determine a surprising amount about the dust itself, its temperature, its size, its composition, and even, in some cases, its age. Space-based observatories, positioned above the distortion and interference of Earth's atmosphere, have proven especially valuable for this kind of research, allowing astronomers to map the distribution of dust across our own galaxy, and even within other distant galaxies, in remarkable detail. But in a few extraordinary cases, scientists have gone even further, actually reaching out and physically collecting samples of dust from space itself. One of the most remarkable of these missions was a spacecraft named Stardust, launched by NASA in the year 1999. Its mission was to fly close to a comet named Wild 2 and capture tiny particles of dust streaming off its surface using an extraordinary material called aerogel, an almost weightless, translucent substance sometimes nicknamed frozen smoke, capable of gently slowing down and capturing fast-moving dust particles without destroying them on impact. In the year 2006, the Stardust spacecraft returned a small capsule to Earth, containing thousands of microscopic grains of cometary dust, material that had likely remained largely unchanged since the very earliest days of our solar system's formation. Scientists continue studying these tiny grains today, using instruments precise enough to analyze particles smaller than the width of a human hair, searching for clues about the earliest chemistry of our solar system, locked away, undisturbed, inside particles of dust that had been drifting quietly through space for over 4.5 billion years, until a spacecraft finally reached out and gently gathered them home. The Stardust mission was not the only effort of its kind. A separate spacecraft named Hayabusa, launched by the Japanese Space Agency, successfully returned tiny samples of dust and rock directly from the surface of an asteroid named Itokawa in the year 2010, followed later by an even more ambitious successor mission that brought back larger samples from a different asteroid roughly a decade after that. NASA's own OSIRIS-REx mission carried out a similar feat, briefly touching down on an asteroid named Bennu and successfully returning a substantial sample of surface material back to Earth. Each of these missions represents an extraordinary amount of patience and precision, spacecraft traveling for years across millions of miles of empty space, executing maneuvers with pinpoint accuracy, all in order to gather what often amounts to only a few grams of material, tiny particles of dust and rock that nonetheless carry within them an enormous amount of scientific value. Preserved records of processes that have long since reshaped and reworked the surface of Earth itself. Deep within the dense, dark clouds of interstellar dust, some of the most striking structures in the entire galaxy quietly take shape. Astronomers call them Bok globules, named after the astronomer Bart Bok, who first proposed in the 1940s that these small, dark, roughly spherical clouds might be the seedbeds of new stars. Bok globules are relatively small by cosmic standards, typically just a light year or two across, but they are extraordinarily dense with gas and dust, dense enough to appear as stark, inky silhouettes when seen against the brighter backdrop of a glowing nebula or a dense field of distant stars. For decades, astronomers could only guess at what was happening inside these dark, opaque clouds, because visible light simply could not penetrate their thick shroud of dust. It was only with the development of infrared and radio astronomy that scientists finally gained the ability to peer inside and confirm what Bok had originally suspected. Deep within many of these globules, dense knots of gas and dust are indeed slowly collapsing under their own gravity. The earliest, quietest stages of star formation, hidden completely from ordinary view. This collapse is an extraordinarily slow, patient process. A typical Bok globule may take hundreds of thousands of years to fully collapse into a young star, or sometimes a small cluster of stars, forming together within the same dusty cocoon. Throughout nearly this entire process, the forming star remains completely hidden, wrapped in a thick cocoon of the very same dust and gas that is slowly feeding its growth. Only in the final stages, once the young star becomes hot and energetic enough, does it begin to disperse the surrounding cloud, gradually emerging from its dusty cocoon, visible at last in ordinary light. Some of the most famous images captured by powerful telescopes show this exact process in progress. Dark, dusty pillars and globules, silhouetted against the brilliant glowing backdrop of star-forming regions, with faint points of infrared light detected deep within them, revealing young stars still hidden inside, quietly gathering mass, still tens of thousands of years away from finally breaking free of the dust that gave them life. Bok globules rarely form in perfect isolation. More often, they are found clustered together within larger star-forming regions, sometimes dozens of them scattered across a single glowing nebula, each one representing a separate individual pocket of collapse, occurring at a slightly different pace and a slightly different stage. Some globules within the same cluster may already contain young stars nearing the end of their formation, while their neighbors, only a short distance away, remain almost entirely quiet, still tens of thousands of years from beginning any noticeable collapse at all. This staggered, uneven timing means that a single star-forming region can remain active, quietly producing new stars for millions of years at a stretch, one globule finishing its transformation just as another, nearby, is only beginning its own long, slow journey toward eventually becoming a star. Astronomers have also found that the mass of a Bok globule tends to determine, fairly reliably, what kind of star it will eventually produce. Smaller, lighter globules typically collapse into stars similar in size to our own sun, or smaller still, sometimes forming objects too small to ever ignite proper nuclear fusion at all, known as brown dwarfs, destined to remain forever dim, cooling slowly across billions of years without ever truly shining. Larger, heavier globules, containing significantly more mass, are capable of producing far more massive, brighter stars, the kind that burn through their fuel quickly and end their lives sometimes only a few million years later, in a dramatic supernova explosion, scattering fresh dust back into the surrounding cloud, ready to begin the entire slow process over again. Cosmic dust is not confined only to the depths of interstellar space. A surprising amount of it reaches all the way to Earth, falling gently through our atmosphere every single day. Scientists estimate that somewhere between 5,000 and 10,000 tons of extraterrestrial dust drift down to Earth's surface annually, an amount that sounds dramatic, but is spread so thinly across the entire planet that it remains almost entirely unnoticed in daily life. Most of this material originates from comets and asteroids, tiny fragments shed as they pass through the inner solar system, eventually crossing paths with Earth's orbit. As these microscopic particles enter our atmosphere, most are simply too small to burn up dramatically the way larger meteors do, producing the streaking light of a shooting star. Instead, they slow down gently in the upper atmosphere and drift gradually downward over a period of weeks or even months, eventually settling quietly onto the surface, indistinguishable to the naked eye from ordinary terrestrial dust. Scientists have developed specialized methods to identify these particles, searching in locations where the arrival of extraterrestrial material is easiest to detect, particularly the pristine ice of Antarctica and the deep, undisturbed sediment layers of the ocean floor, places where ordinary earthly dust accumulates slowly enough that even a tiny fraction of extraterrestrial material can eventually be identified and studied. Under a microscope, many of these particles reveal telltale signs of their origins in space. Tiny, glassy, partially melted spherules, formed as the particle briefly heated during its passage through the atmosphere, along with characteristic chemical signatures rarely found in ordinary terrestrial minerals. In a very real, physical sense, a small amount of interplanetary dust settles gently around you nearly every single day, drifting silently down through the atmosphere, mixing invisibly with the ordinary dust of Earth, completely unnoticed. It is a quiet, continuous reminder that even here, in the familiar comfort of home, we remain connected to the wider universe, receiving a slow, steady trickle of material that has been drifting through space for a very long time indeed. This gentle rain of dust is far from a modern discovery, though understanding its true origin took scientists a surprisingly long time. For centuries, occasional reports of unusual dust deposits, sometimes noticed after certain meteor showers, were recorded without any clear scientific explanation. It was not until the 20th century, with the development of sensitive analytical chemistry and electron microscopy, that scientists could conclusively distinguish extraterrestrial dust from ordinary terrestrial particles, based on subtle differences in mineral composition and isotopic ratios rarely found together in rocks that formed here on Earth. Researchers studying deep ice cores drilled from Antarctica have even been able to track subtle variations in the rate of dust infall over thousands of years, occasionally correlating brief spikes in extraterrestrial material with specific known events, such as the breakup of a particular comet or an unusually close pass of a known asteroid stream, offering a kind of slow, patient historical record, written not in ink, but in the quiet accumulation of ancient dust lying walking above it. The deep ocean floor offers a similarly patient archive. In certain slow accumulating regions of the seabed, sediment builds up so gradually, sometimes only a few millimeters every 1,000 years, that even tiny, rare particles of extraterrestrial dust can remain identifiable within distinct sediment layers for millions of years after they first settled there. Researchers extracting long cylindrical cores of this ancient seafloor mud have, in a handful of remarkable cases, identified distinct bands enriched with extraterrestrial material, thought to correspond to specific ancient events, a nearby supernova explosion tens of millions of years ago, whose expanding debris eventually rained down gently onto Earth, leaving behind a faint, patient signature, buried quietly within the ocean floor, waiting patiently to down. Not every grain of cosmic dust follows the same story we have described tonight. Some grains are especially remarkable because they are older than the sun itself. Scientists call these presolar grains, tiny particles that formed around other, ancient stars, long before our own solar system began to take shape, and that somehow survived, essentially unchanged, through the entire violent process of our solar system's formation. Finding these ancient grains is extraordinarily difficult, because the vast majority of dust that went into building the sun and planets was thoroughly melted, mixed, and chemically reprocessed during that early, chaotic period. Only a very small fraction of the original interstellar dust managed to avoid this fate entirely, becoming trapped instead within primitive meteorites, essentially frozen in time, preserved from the moment they first arrived in the young solar nebula. Scientists identified these presolar grains by carefully examining the ratios of different isotopes, variant forms of the same chemical element, within tiny mineral particles extracted from meteorites. Material that formed within our own solar system tends to share a fairly consistent isotopic signature because it all originated from the same well-mixed cloud of gas and dust. Presolar grains, by contrast, often show dramatically different isotopic ratios, chemical fingerprints that simply do not match anything formed within our solar system, but that closely match the predicted output of specific, very different types of ancient stars. Some of these grains are made of silicon carbide, others of pure carbon in the form of microscopic diamonds or graphite. By studying their precise chemical composition, scientists can often identify, with remarkable confidence, the general type of star that originally produced each individual grain. Sometimes a dying red giant, sometimes a supernova, sometimes an even more exotic and violent stellar event. Some of these presolar grains have been dated as being billions of years older than our solar system itself, meaning that within a small meteorite, sitting quietly in a laboratory drawer here on Earth, there exist tiny fragments of stars that lived and died long before the sun was ever born. Holding such a meteorite in your hand, you would be holding, quite literally, a small piece of a star that no longer exists, material older than our own sun, older than Earth, older than everything you have ever known, patiently waiting, all this time, simply to be found. The particular meteorite, where many of the most well-studied presolar grains were discovered, fell to Earth in the town of Murchison, in Australia. In the year 1969, scientists quickly recognized it as an especially primitive type of meteorite, one that had experienced remarkably little heating or chemical alteration since the very earliest days of the solar system, making it an ideal place to search for material that might have survived from an even earlier era still. Over the decades since its discovery, researchers have returned to samples of the Murchison meteorite again and again, using increasingly sophisticated laboratory techniques, extracting and identifying thousands of individual presolar grains, some measuring only a few thousandths of a millimeter across, each one a tiny, durable survivor from the winds of some ancient, long-vanished star. It is a strange thing to consider that a single rock, falling from the sky on an ordinary afternoon in 1969, could contain within it material old enough to predate the very sun that lit that afternoon sky, quietly carried across billions of years, simply to land, almost by chance, in a place where curious scientists happened to be watching, and waiting, and ready to look closely enough to notice. On the grandest scale, cosmic dust plays a defining role in shaping the appearance and structure of entire galaxies. When we look at photographs of spiral galaxies, similar in shape to our own Milky Way, one of the most striking features is the elegant, sweeping pattern of their arms, often outlined by dark, dusty lanes weaving gracefully between bright regions of active star formation. These dust lanes are not simply decorative. They mark the locations where gas and dust are actively being compressed, as the galaxy's spiral pattern slowly rotates through the disk, triggering new waves of star formation as it moves. Within our own galaxy, this same effect shapes what we can and cannot see from Earth. Looking toward the dense, crowded center of the Milky Way, we do not actually see the galactic core directly in visible light, because a thick band of interstellar dust, spread across thousands of light years, almost completely blocks our view. For centuries, astronomers had no way of knowing exactly what lay at the heart of our own galaxy, hidden entirely behind this vast curtain of dust. It was only with the development of infrared and radio astronomy, wavelengths of light capable of passing more easily through dust, that scientists finally managed to peer through the haze and confirm the presence of an enormous black hole, millions of times the mass of our sun, sitting quietly at the very center of the galaxy, patiently orbited by a dense swarm of stars, hidden the entire time behind an ordinary, unremarkable cloud of cosmic dust. The same dust also plays a subtler, quieter role throughout the galaxy, gently scattering and reddening the light of countless faraway stars. an effect astronomers call interstellar extinction. Light traveling toward Earth from a distant star must pass through varying amounts of dust along the way, and blue light tends to scatter more easily than red light, meaning that stars viewed through a thick layer of dust often appear noticeably redder and dimmer than their true, actual color and brightness. Astronomers must carefully account for this effect in nearly every measurement they make of distant objects, correcting for the subtle influence of dust scattered somewhere along the vast distance between us and whatever star or galaxy they happen to be studying. A quiet, persistent reminder that even the light reaching our eyes tonight has likely traveled through clouds of ancient dust along the way. This same scattering effect extends far beyond our own galaxy, shaping how we perceive countless distant galaxies as well. Some galaxies, viewed nearly edge-on from our vantage point on Earth, display a strikingly thin, dark band running directly through their bright, glowing disk, the combined shadow of countless dust clouds, all aligned roughly along the same flat plane where the galaxy's stars and gas are concentrated. Other galaxies, richer in gas and dust, and actively forming stars at a rapid pace, can appear dramatically dimmer and noticeably redder in visible light than their true underlying brightness would suggest, simply because so much of their light is being absorbed and scattered by dust before it ever has the chance to reach our telescopes. Astronomers studying the most distant, earliest galaxies in the universe must account for this effect with particular care, since even modest amounts of intervening dust, scattered across billions of light years of intergalactic distance, can meaningfully distort our understanding of how bright and how large and how old these ancient, faraway galaxies truly are. There is a simple, often repeated phrase in popular science that we are made of stardust. It is a phrase that can sound almost like poetry, a pleasant metaphor rather than a literal scientific fact. But it happens to be entirely true, in the most direct and precise sense possible. Every carbon atom in your body, every oxygen atom you breathe, every atom of calcium in your bones, and every atom of iron carried through your bloodstream was formed inside the core of an ancient star, through the slow process of nuclear fusion, and later released into space as dust when that star reached the end of its life. That dust drifted for millions, sometimes billions of years, through the quiet emptiness between the stars, before eventually becoming part of the cloud of gas and dust that collapsed to form our own solar system. Some of it became part of the sun, some of it became part of Earth, and a very small portion of it eventually became part of you, rearranged countless times along the way, first into rock, then into soil, then into the plants and animals that eventually became the food that built your own body, atom by atom, over the course of your life. This is not simply a poetic idea. It is a direct, traceable, physical fact, confirmed repeatedly through decades of careful research in nuclear astrophysics, tracing the specific elements found throughout the universe back to the specific nuclear processes occurring inside dying stars, capable of producing them. In a very real sense, every one of us carries, within our own bodies, material forged inside stars that lived and died long before the sun itself ever existed, scattered as dust across the galaxy, drifting patiently through the darkness, until it eventually found its way here, into the particular, temporary arrangement of atoms that happens, for now, to be you. There is something quietly humbling in that thought. The same physical process that built the ground beneath your feet, and the mountains, and the oceans, also built the atoms currently reading these words, currently breathing, currently resting here, at the end of a long day, in a body assembled, patiently, from the ashes of stars that finished burning long before this particular arrangement of stardust ever learned to call itself by a name. This idea was first articulated clearly, in scientific terms, by the astronomer Carl Sagan in the 1970s, though the underlying nuclear physics behind it had been worked out gradually over the preceding decades by researchers studying exactly how elements are forged inside stars. Different elements within your body have different stellar origins. The lighter elements, hydrogen in particular, trace their origin all the way back to the earliest moments of the universe itself, formed in the first few minutes after the Big Bang, long before any star had even begun to form. Carbon, oxygen, and nitrogen, by contrast, were built later, inside the cores of ordinary stars similar in size to our own sun, through the steady process of nuclear fusion occurring over billions of years. The heaviest elements, gold, platinum, and many others, required even more extreme conditions to form, likely forged during the catastrophic collisions of neutron stars. Extraordinarily dense stellar remnants, in events so violent and so rare that scientists only confirmed this particular origin story within the past decade, through the direct detection of gravitational waves rippling outward from one such collision. As we come gently toward the end of our time together tonight, let us sit for a moment with the strange, quiet patience of cosmic dust. A single grain, drifting through interstellar space, has no sense of urgency. It does not hurry toward a destination. It simply drifts, following the slow pull of gravity, for as long as it takes, sometimes for millions of years, before finally becoming part of something larger, a star, a planet, or perhaps, eventually, a small part of a living thing, somewhere, resting quietly at the end of a long day. There is a kind of lesson hidden in that patience, if you are willing to sit with it for a moment. So much of what feels urgent to us, in the middle of an ordinary day, a deadline, a worry, a small disagreement, would not register at all on the timescale that cosmic dust operates within. Not because those things do not matter. They matter very much, within the small, precious span of a single human life. But there is something quietly comforting in remembering that the universe itself is in no hurry. It took hundreds of thousands of years for a single grain of dust, deep within some ancient molecular cloud, to slowly become part of a star. It will take billions of years more for that same material to be recycled again, scattered once more into space, eventually becoming part of some future star, some future planet that does not exist yet and will not exist for a very long time. You are allowed to borrow a little of that patience tonight. You do not need to rush towards sleep. You do not need to force your mind to quiet down all at once. You can simply let your thoughts settle, slowly, the way dust settles gently through still air, drifting downward, without effort, without hurry, until it finally comes to rest. Let your breathing continue at its own unhurried pace. Let your body remain heavy and still, exactly where it is. There is nowhere you need to be right now, except exactly here, resting, patient, unhurried, the same way a grain of ancient stardust rests quietly in the dark, waiting, without any concept of time at all, for whatever comes next. Consider for a moment how much has already happened, quietly and patiently. Simply to allow this exact moment to exist, stars had to live and burn and eventually die, scattering their contents into space. That scattered material had to drift, slowly, for millions of years, before gathering once more into a new cloud. That cloud had to collapse, gradually, into a new star, surrounded by a spinning disk of leftover dust. That dust had to gather itself, patiently, grain by grain, into a small, rocky planet, orbiting at just the right distance from its star. And on that small planet, across billions of years, simple chemistry had to slowly become something more complex, eventually becoming the particular arrangement of atoms currently resting here. Reading these words, breathing slowly, preparing for sleep. None of this needed to happen quickly. None of it needed to be rushed. Every single step took exactly as long as it needed to take, and not a moment less. You too are allowed that same unhurried timeline tonight. As we slowly drift back now, from the vast, quiet clouds of interstellar dust, from the ancient grains older than the sun, from the faint, silvery glow of zodiacal light rising softly above the horizon, let everything we explored together tonight settle gently into your mind. We began with dust that seems too small to matter, and found that it built stars, planets, and eventually, every atom within our own bodies. We followed dust from the death of ancient stars, through the slow collapse of dark, quiet clouds, into the birth of new stars and new worlds. We considered the faint glow of dust drifting through our own solar system, and the extraordinary journey of a spacecraft that reached out across the darkness to gently gather some of it home. We met grains of dust older than the sun itself, preserved quietly inside meteorites, and we thought about the dust that drifts down through Earth's atmosphere, settling silently around us, nearly every single day. Through all of it, one idea remained close. Nothing here is wasted. The dust of a star that died billions of years ago becomes the raw material for a new star, a new planet, a new beginning. Endings in the universe are rarely truly endings. They are simply quiet transformations, patient and unhurried, taking exactly as long as they need to take. There is nothing more you need to hold on to tonight. Let that dust continue its slow, patient drift somewhere far above you, in the quiet dark between the stars. Let whatever thoughts remain from today drift away too, just as gently, just as patiently, and let yourself sink deeper into a slow, unhurried rest of your own. Exactly the kind of rest you are allowed tonight, without needing to earn it, without needing to rush toward it. The universe continues its own slow work out there tonight, but right now, there is nothing you need to do. Just rest, just stillness, just you resting quietly, made, in the most literal sense possible, from the patient, ancient dust of stars that finished shining long before you were ever here to look up and wonder about them. Somewhere, right now, in some distant corner of the galaxy, a new molecular cloud is beginning its own slow collapse, following the exact same patient process we followed together tonight, that will not finish for hundreds of thousands of years yet. And somewhere else, an old star is quietly shedding its outer layers, releasing fresh dust into the darkness, adding, slowly, to the very same reservoir of material that eventually became the ground beneath you, the air around you, and the body currently sinking, heavier and heavier, into the comfort of your bed. This has been happening for billions of years, and it will keep happening for billions more, long after tonight, long after this particular night's rest has ended and given way to tomorrow, and the day after that, and all the ordinary days that will eventually, quietly, become memories, the way starlight fades gently behind a horizon. None of that needs your attention right now. It will happen exactly as it needs to happen, whether you are awake to think about it or not. If you are still here with us, another quiet journey is waiting for you, on some other evening soon. And if tonight's journey helped carry you a little closer to sleep, a like, a subscribe, or a gentle comment helps other tired minds find their way here too. There is nothing left to think about tonight. There is nothing left to plan, or solve, or worry over. Just this quiet room, this soft darkness, and the slow, steady rhythm of your own breathing, carrying you gently further and further from the day that has already, quietly, let you go. Somewhere above you, invisible in the darkness, ancient dust continues its slow drift through the space between the stars, patient, unhurried, taking exactly as long as it needs. You are allowed that same patience tonight. You do not need to hurry towards sleep. You only need to let go, gently, the way a grain of dust settles slowly downward through still, quiet air, drifting, without effort, until it finally comes to rest. Let your body remain heavy and warm and still. Let your thoughts continue to soften and fade and drift apart, like distant starlight scattered gently through a thin, quiet haze. Whatever tomorrow holds, it can wait. Whatever remains unfinished tonight, it can wait too. Think back, for just a moment, to where we began this evening, with a single grain of dust, smaller than anything your eye could ever hope to see, drifting quietly through the space between the stars. That grain did not know it would one day become part of a planet. It did not know it would one day become part of a person, resting in a warm bed, listening to a quiet voice describe its long, unhurried journey. It simply drifted, patiently, for as long as it needed to, trusting nothing at all, because dust does not trust, or hope, or wonder. It simply continues, one slow moment after another, until enough of those moments finally add up to something new. You are allowed to rest in that same unhurried way tonight, not forcing sleep to arrive, not measuring how long it is taking, simply drifting, the way that dust drifts, patient and unbothered, letting the night do its own slow, quiet work, however long that happens to take. For now, there is only this room, this breath, and the slow, patient dark, settling gently around you, the same dark that has cradled dust and stars and quiet worlds for billions of years, and that now, for tonight, simply holds you too. From the sleep journal, and from one tired mind to another, across the soft, patient dark of tonight. Sleep well, rest gently, and good night.